The goal here today with this webinar is to show off some case studies as well as talk a bit about the history behind using microfluidics for this application and some of the new methods that have been developed very recently that really change how people think about using this technology for getting deeper insights into the enhanced oil recovery process. Before we get into that though, the quickest intro to interface that I can give is that our goal is to make the interactions and properties of reservoir fluids truly accessible. What that means to us is that understanding how the fluids that we inject into reservoirs, especially in the enhanced oil recovery scenarios, has traditionally been a very challenging data set to get a hold of, and really even more challenging to get experimental data and interpret that data to make a good decision in the field. At Interface, we want to make that it's simple to get more data that's more repeatable to make a better decision about how your chemistry is going to interact. Now, in the enhanced oil recovery engineers toolbox, there really are four primary tools that are used. The first and most common is your core flood. This is the most common experimental tool used in order to optimize, in particular, polymer floods. Now, core floods are a very excellent tool. They've been around for almost 100 years now, and Interface really does build on the legacy of core flooding for a lot of the technology that we have. Moving out of the sort of real experimental data set world, we're now dealing with things like analytical modeling software, looking at analogous reservoirs and analogous operating processes, as well as using commercial simulation tools from a variety of technologies that are out there. So the real question then goes back to, why are we doing lab work in the first place? First of all, fluid compatibility is known to impact the performance of enhanced oil recovery polymers very significantly. There's extensive literature. I've cited a few papers there, but understanding how water and chemistry interact is the #1 way to optimize a polymer flood or other enhanced oil recovery project. Chemistry that gains viscosity typically is highly dependent on the composition of that water. And so finding good water sources and understanding those water sources really does impact your performance. Second is that analytical and statistical methods that are very effective do rely on assumptions and measurements that must be tuned using empirical data. So getting a good model really does require good input data, and getting good input data has traditionally been very, very expensive, primarily coming from things like core floods or straight from vendors. The third thing is that often doing lab work, when we look at the total cost of actually getting the data, is less costly than simulation, especially with Interface's technology, where we're getting about 10 times more data than you traditionally have from traditional lab work. You're going to spend less for better data. And finally, using real fluids incorporates the complexity that is very challenging to actually capture in a simulation program. The nuanced changes in oil composition or water composition over time is really challenging to model accurately, especially without having good data in the first place. And so whether or not you think you're controlling for it, at least if you're using real fluids at real temperatures and pressures, you get real reactions that may or may not have been captured in those simulation software. So empirical data does capture things that simulation cannot capture. And so microfluidics is really the topic of the day, and how does microfluidics actually work? This is a technology that's been around for more than 70 years now, with the first ever application of microfluidics actually being understanding a water flood. So that's the cover page of a paper published in 1961, which is the first one of the first commercial papers ever published on microfluidics as a technology. And really what it is understanding how fluids flow at the micrometer or nanometer scale, which is identical to the scale that we deal with in reservoir applications, which is why it fits so nicely with this application. By utilizing precise instrumentation, we're able to perform experiments using volumes of fluids that are not really comprehensible at any other scale. So being able to do experiments with very, very tiny fluid volumes very, very accurately is the main strength of microfluidics. Now, this technology has since been adapted by the biomedical industry, and that industry has run with it and fundamentally changed everybody's lives for the better over the last 70 years. So some perfect examples are, rapid COVID tests are a microfluidic device. Pregnancy tests are microfluidic devices. Diabetes management strips are microfluidic devices. All of these devices have improved outcomes for both patients and disease management over the last 70 years since this technology was invented. And now Interface is taking the advancements that the biomedical sector has really put forth and bringing them back into the oil and gas sector. And we're using what we now call reservoir analogues to understand how fluids flow through porous media. So the goal here is to create a two-dimensional porous media that has the same permeability, pore size, porosities, grain size distributions, and most importantly, wettability of the reservoirs in question. So we're going to be showing examples, two examples today where we've taken highly customized porous media specific to our customer's application and looked at how that compares to results in other lab work like core floods and other field applications where we're looking at real world well production. So the key features of microfluidic EOR is that this is the only way to get real-time visual access to pore scale fluid interactions. So we actually see fluid front displacement advancement, we see pore throats trapping behavior, we see bypassing, and we can quantify all of those. The second is that the speed of testing that we're dealing with is significantly faster and significantly easier than your traditional core floods, for example. We're making one measurement per day. Your core flood is making about a measurement per week or every 2 weeks. Now, repeatability is a thing that microfluidics really excels at because the only way to get truly repeatable porous media data is through controlling your porous media, which is not possible with traditional core floods, and microfluidics opens the door to this. And finally, customization is really critical to getting a good data set. As we know in almost all aspects of trying to predict flow through porous media, getting a custom idea of how our porous media and how our reservoirs behave is critical to getting good predictions. The same is true here. So spending the time upfront to make custom reservoir analogs for our clients is something that really makes a big difference in the results. And it's something that Interface is uniquely positioned to do because we are the only fully vertically integrated microfluidics company serving this industry, which means actually developing a custom reservoir analog doesn't cost our customers anything. It's not something we charge for, it's just a part of the process. And so the question is, how do you run a microfluidic experiment to do EOR experiments? So what you can see on the right there is an image of a close-up of one of our devices. You can see we've got the microfluidic device inside of a manifold that holds that device. And on the left side is a schematic of the system. So the way we run these experiments is first we saturate the porous media with brine from the reservoir. We then displace that brine with crude oil of interest. We displace that to the point where we have a representative initial saturation of that oil-water ratio. And then we're going to run either further water, polymer, or combined water-polymer floods to understand how displacement works, recovery factors, and any sort of pore scale interactions that we can capture. As I said, we use, we have direct visual access to the porous media, which means we're able to see things happening in real time. And to give you an example, almost all of the images you're going to see today are going to be in a style that looks like on the left side there, where we're using the natural fluorescence of the oil to understand where the oil is and is not, for example. So it gives us a very good quantification of how much fluid is in any one pore space at any given time. By combining that with bright field, or basically visible light photography and microscopy, we get the ability to understand how solids or how non-oil phases interact. And so by combining fluorescence and bright field, you get this holistic picture of how is my fluid system responding during production. And before I mentioned how important it is to get wettability correct, wettability is a primary impactor on recovery, as we all know. And so making sure you get initial conditions as well as representative reaction from the porous media is very important. And so what we have is the ability to tune the wettability of our microfluidic systems to be representative of our clients' reservoirs. So if you're looking at a oil wet reservoir versus a water wet or something intermediate in between, then we can tune our system to be representative of that. So I mentioned before that we do almost all of our data collection through image analysis and through video analysis and machine vision. So what that workflow actually looks like is we start with a raw image. So the raw image that you see on the screen here, this is what our camera captures. And you can see the bright white, that's your oil fluorescing. And then all the dark channels are where the water or polymer has displaced that oil. In order to understand and quantify that recovery and saturation, we then convert that image to a binary image so that we know exactly where the oil is and is not. And we have a quantifiable process for saying exactly how much oil is in there. Now, what we do is we then go back and we mask back in where all the channels were so that we know where all the water saturation is. So now we can quantify water, oil, and pore volumes. And then to help interpret those data, we then go in and add false colors to give our human brains a little bit of a better chance to interpret what we're looking at. Because there's one thing we've learned at Interface is that humans are terrible at looking at a picture and understanding and quantifying what's going on, and machines are great at it. So this completed false color process is actually more of a process for helping us as folks that need to interpret these results look at it and understanding what's happening. So for what you're looking at here is that purple image. The purple in this color here is how much additional oil production was gained after, this is your post water flood. And then after we run a polymer flood, we see the purple is all the additional oil production and which pores it was produced from. So getting into that quantification, what are the things that we're measuring at Interface? First is sweeping efficiency or recovery factor. So these data sets allow us to understand pore scale dynamics, which allows our engineering clients to optimize their EOR process. Recovery factors in core are measured typically volumetrically or gravimetrically, whereas at Interface, we measure our sweeping efficiency visually. So we look at where was the oil and where is the oil not now. In a core, often we're adding pressure taps or sampling points to try and understand how front advancement proceeds or other dynamic processes during the flood. And X-ray or CT scanning techniques can show this, can allow us to capture this data, but there's a few drawbacks being cost and the lack of pore scale resolution. So microfluidics really does address the need to understand pore scale front advancement. And so I'll show you an example of what that looks like here. So what we're looking at here is we partnered with a polymer manufacturer who had run a long history of core floods, and we're looking at replicating the core floods on our systems. So if I play the video, what you're going to see is that on the top, we have a high molecular weight polymer displacing the oil, and on the bottom, a low molecular weight polymer. And as the video plays, we're having a real-time visual of how much oil is produced by each of those products. And if I go back and replay this video from the beginning, what we see is that the way that these polymers displace and the behavior, the pore scale is significantly different, where we have nice piston-like displacement with a low molecular weight polymer and a more fingering type of displacement with a high molecular weight polymer. So understanding the dynamics here is really one of the main benefits, in addition to just understanding how much production we have. As you can imagine, though, when you have different fingering behaviors, you start to look at questions like bypassing and conformance control. So mechanisms of increased production require the highest possible resolution, leading to ever increasing complexity and cost in your core floods. So trying to elucidate what's happening inside those pore throats really does add a significant amount of complexity to gathering experimental data. But like I said before, microfluidics provides this unprecedented direct visual access to quantify and understand it. Going beyond understanding just fingering effects and displacement characteristics, we can actually quantify trapping of different phases, whether that's oil or water, as a function of the chemistry or pore throat geometry. And I'll show you some images of that in a minute here. And finally, obviously, just being able to incrementally understand oil production. So for example, this image here is the same experiment as what I just showed you a few slides ago. But what we're looking at now is we've colored this, where any green pixel is a pore or pore throat that has never seen aqueous phase. So if it is colored green, that is trapped oil. If it is colored blue, that pore or pore throat has been swept by water or polymer. And if we're looking on the right, we can quantify how this behaves as a function of pore throat size. So in unswept pores, we're typically looking at the majority of our pores that are in the range of 10 to 11 microns of hydraulic diameter. We're seeing greater trapping at a pore throat size of 10 to 11 microns than any other area. Whereas pores of the 9 to 10 micron pore throat size are more likely to be swept. So again, this is a new kind of analysis that is not possible with traditional core tools, and it does give us a good idea of what's going on. And so we can see, the high molecular weight polymer, while it does produce a lot more oil, it also has very high oil trapping. If we take this to sort of the next logical step of understanding how different porous media with different fluids behave, we published a paper last year looking at how we look at multiple porous media with different permeabilities and porosities stacked on top of each other in fluid communication. So what we're looking at here is the top porous media is high perm, high porosity. The bottom is low perm, low porosity. And we have sort of a medium high and a medium low of each between. The goal was understand and quantify how we can bypass or not bypass or access additional unswept regions with different fluids. So we can see before breakthrough, we have pretty even displacement, but as soon as we have breakthrough, we get really very little additional fluid produced through the low permeability regions. Once we switch from a water flood mode to a polymer flood mode, you can see that the change in viscosity of the fluid really does dramatically increase production from all four zones. And so we want to understand how do we access challenging regions or improve our conformance. This is a tool that can be used to quantify what's going on. I see a few questions that come in the chat here. I will get to those questions at the end of the presentation here, which shouldn't be too long. So again, if we want to dig even deeper into these front advancement diagnostics, we want to look at understanding viscous fingering, potential for early breakthrough, and other characteristics like that. So what we can do at Interface is actually start doing analysis. This is similar to adding a pressure tap along the core, but doing analysis visually of each section of the porous media as we produce. So what you'll see is on the left, we're producing, again, the same data that I showed you a few minutes ago. But if we look at the results as a function of your multiple zone analysis here, we can see that viscous fingering effects really come across, where we're producing from all 4 zones or all 5 zones all at the same time. So when we see the lines all clustered together like this, this is very indicative of sort of a fingering behavior in the production. If we then look at the bottom where we see nice piston-like displacement, there's a significant distance between each of these lines. And so that distance really does represent piston-like displacement. And as we get to closer to the end, we see more viscous fingering, which if we back up our video is exactly what we see. We see a finger develop, and then now we've got production happening from all 4 or all 5 zones at the same time. So again, this is an unprecedented level of understanding of which zones are producing. So with that, that's sort of the background of the technology. I will take a second here to just answer a couple of questions that have come in. So first question is how to customize the permeability of microfluidics, typically higher than rock cores. I would say that that's not an accurate expectation. We can mimic permeability in our system. I shouldn't say mimic. We create systems that have the same permeabilities as the real rock. So our systems, we've created everything from sort of nano-Darcy permeable systems for unconventional reservoirs, all the way up to multiple Darcy systems for conventional, and everything in between. So there's really no limitation on permeability that we can create. The way we customize that is by modifying the pore throat sizes as well as the porosity. And then we apply pressure to the system by using high accuracy, high performance pumps. So we have, similar to how you'd use pumps on a core flood, we've just got basically much fancier pumps that operate at much lower flow rates and things like that, with higher accuracy both on flow rates and pressure control. So we just use fancier pumps. So that's the questions that have come in so far. Now I'll talk a bit about our relationship with Baytex, and I'll just start off by saying thank you to Baytex for allowing us to share this data. At the end, I'll have the reference to the paper that was done here. We published it just a few weeks ago. So if anybody's interested in that paper, the reference will be available at the end. So the background here is that Baytex has been conducting a polymer flood in their Lloydminster sandstone formation since 2018. They've been optimizing this polymer flood for injectivity performance and economic performance throughout the life of this flood. And the hypothesis that they had was that reducing polymer viscosity would not negatively impact production from the flood after it had been aging for a period of time. But this is a costly and expensive change to make. And so they were seeking additional data to understand how the behavior would change if they changed viscosities. So they came to Interface as well as some of their simulation partners, and together we collected a significant amount of data. So we performed microfluidic experiments with different scenarios of polymer viscosity of 20, 30, and 50 centipoise in both tertiary and secondary production modes, so post-water flood as well as just initial polymer flood. And that, like I said, they did a bunch of analytical experiments and statistical modeling as well to understand how if the microfluidic experiments would be predictive of both field performance as well as simulated field performance. So as I said before, getting a custom reservoir analog that is designed to replicate their system is extremely important. So we spent a lot of time up front obtaining data in order to create this representative porous media that you can see on the screen here, and it has a fairly significantly different look to the ones I've shown you previously. We also ensured that at the starting of each experiment, we had a representative oil-water saturation. And you can see the sort of specs here. So we were running the experiment at reservoir temperature, which was 23 degrees Celsius. The viscosity of the oil was 3,500 centipoise at 20 degrees Celsius. The channels in the analog were 14.7 microns with 22.7% porosity and a 78.5% plus or minus 1% saturation of your oil. You can also see the grain size distribution. So we received that data from Baytex, but they got that from an external laboratory, provided that to us, and we created an analog that represented the same pore throat size distribution. So that was really important. Again, I showed you this experimental setup before, but the really critical, we ran 3 primary experiments for a number of fields. First was in just a single injection of polymer, and then we also followed it up with a water flood with a polymer post flood. And you can see the injected fluid that we were looking at here. So recovery factors ranged from about 46% up to 70%. And ultimately, the long story short is the final recovery factors that we were predicting lined up very, very well with what was seen in the field, as well as what was seen in the simulation programs. So the first experiment I'll show you here is a comparison of a water flood to a polymer flood. And I'll play the video. Just let folks watch. So this exhibits very typical expected behavior where we have water fingering through the analog and producing significantly lower oil volumes. The interesting thing that we can compare here, and one of the interesting findings, is if we compare the trapped oil, we see in the polymer flood, we see quite a bit of small volumes of oil trapped in the pore throats in some areas. And then we don't see that same behavior up in the water flood area. And that's just one aspect of what's going on there. Can we investigate that further? The second experiment, once we saw that the water flood and the polymer flood were behaving as expected, a comparison between 50 centipoise polymer and 20 centipoise polymer was performed. The goal, again, just to remind you, is Baytex is asking the question, I'm spending a lot of money on my polymer. Am I spending too much money on this polymer? Or can I safely reduce this polymer viscosity? Because if I can save significant cash on our chemistry spend each year. And what we can see here, if we look at the production on the right, is that if you're concerned about initial production, a higher viscosity does produce more oil more quickly. But after approximately 1 pore volume of fluid injected, you're going to plateau at oil production between, there's really no difference between the 20 centipoise polymer and the 50 centipoise polymer. And that means that if you've already been injecting, we would expect you to be able to safely reduce your concentration. And then, as I said before, we wanted to be able to compare a water flooded system to a polymer flooded system. So again, we can see we performed that water flood again, and then followed it with a slug of polymer. And this is where you get some really unique insights from the microfluidics, because the ability to see new production and new displacement really is unique. That purple color is not something you can get from any other system. So that incremental production as a function of pore throat, trapped phases, all of that really is unique. And that's something Interface developed for this project. It is not something that we had before. And finally, again, we talked about it before, but being able to do simple front analysis and being able to understand how that recovery behaved, as if whether it was a viscous finger or sort of a more piston-like displacement. So just to summarize the results here, on the single injection tests, we ran half pore volume, 1 pore volume, and about 1.5. You can see the amount of time it took to actually perform these experiments and the ultimate recovery from your water flood, followed by your polymer flood. So our increased recovery from adding a polymer flood after a water flood was between approximately 30% recovery factor increase, but had some variability based on time and pore volumes injected, as well as the initial saturation at the start of each section. When we look at the tertiary injection mode, again, the incremental production is lower, but that's to be expected. As you can see, this is just an excerpt from the production data that Baytex provided in the paper. And you can see here the different sections where they're injecting 50 centipoise polymer from 2018 onwards. And in 2019, they switched from 50 to 30 centipoise polymer. The question is, can we go safely to 20 centipoise polymer? And we can see we really had no impact on production throughout that entire process. There's a lot more data from Baytex in the paper here. So this SBE 212760 can be accessed by anybody with access to One Petro, and really get into the nitty-gritty of their field design and their flood design. So overall, the results here is that the analytical models, microfluidics experiments, were both able to predict the EOR within the required precision for Baytex to make an investment decision. The experimental results were also used to tune those models to better mimic field behavior. And that tuning relative permeabilities, which is sort of a standard tuning parameter, was not enough to actually effectively mimic the field results. And that other phenomenon were required to be incorporated into those models in order to achieve representative behavior. So finally, what was their decision? Ultimately, polymer concentration was reduced by about 60%. Over the course of the process, over the last year since we finished the work. There's been no detrimental effects on production. And overall, the project achieved approximately a 16x return on cash invested with Interface. So in terms of the amount of money saved or cost displaced, this was a good investment on Baytex's side. So finally, just to wrap up our session today, Interface is not just about enhanced oil recovery and polymers. You can apply this method and this type of thinking to all aspects of flow through porous media, whether that's hydraulic fracturing fluid, looking at formation damage, onshore and offshore, looking at PVT and phase behavior, obviously EOR. Carbon storage is a thing we're being asked about more and more these days, because carbon storage is really just a gas injection into a water aquifer instead of a water injection into an oil reservoir. And then we also do custom studies. So a lot of folks will come to us with specific requests or specific problems that they have, and we work with them to identify issues. Some examples of that are production chemistry challenges with emulsification, looking at wax and asphaltene appearance conditions, other sort of wacky questions that they have. So again, I'd just like to say thank you first to Baytex for allowing us to collaborate on this and publish the results. And second, this presentation was originally given at the Canadian Heavy Oil Association breakfast last month. And so again, I say thank you to them as well. With that, I'll open the floor up to any questions. So can we model polymer adsorption effects is the first question. I would say we don't have to model it. This model does accurately capture polymer adsorption onto the surfaces. That's part of the reason that the process does work inside of microfluidics. One thing I didn't touch on before is if we're dealing with a sandstone reservoir, for example, like what we've seen in this case study today, our model is also a silicon dioxide based surface. And so the actual geochemistry is fairly well represented. And so the way that the polymer adsorbs onto sand versus adsorbs onto our micromodels is, I'm not going to say exactly the same, but it is, I would say, representative of that system. So we do see, for example, in our formation damage testing, that we've been able to see polymer reducing the effective hydraulic diameter of the pore throats in our systems, which is the expected behavior for these polymers. Would you see possibility to simulate carbonate cores in microfluidics? Yes, we have done carbonate systems. As you can imagine, our system is not a reactive system, and so the actual rock fluid interaction is not something that we, I would say, typically are trying to capture. The goal of microfluidics really is the ability to isolate your fluid-fluid interactions from your fluid-rock interactions. Now, there are some situations like polymer adsorption where the fluid-rock interaction is fairly representative, but if you want to understand, for example, the reactivity of a carbonate reservoir, this is not a tool that you would use for that. There's still absolutely a good place for a lot of your core floods. But the way we typically recommend folks to think about it is, let's recreate the carbonate system in terms of a porous media on our reservoirs, run a series of screening experiments to understand fluid-fluid compatibility, so that when you do move on to a core flood, you're able to identify that, well, we know the fluids are compatible in a non-reactive system, but when we put them into the reactive carbonate system, now maybe they are less performative than we would expect. And so we need to find something that is, we know that the fluid system is not the issue, it's the rock compatibility that's the issue. And there's really no other tool that allows you to disaggregate fluid-fluid compatibility from fluid-rock compatibility. I would say that third question that you brought up here about different mineralogies and different absorption and retention rates is something that people in the microfluidic space have investigated. But I'd need to understand the specific case more. I would not say yes or no. We can look into it and understand sort of the root of that, what you're trying to understand when that comes to that question. Excellent. Well, thank you, everybody. Have a great afternoon, and we'll speak with you all very soon.